back, everybody. And thanks for being here despite the less than fantastic weather. We're also going to talk about weather today, so comes handy. So this week is what you can see in the sky, so naked eye astronomy. So maybe something that you were expecting most of the class to be. It isn't, but this is how we all got started as a species thinking about celestial phenomena because, hey, we can spot some in the sky. And we're going to start with the moon, basically with the sun-Earth-moon system. We talked about that already when we talked about tides, so really where the seasons comes from, where the lunar phases come from. Some of that might be familiar because I think some of these things are done in school, but I can never count on this having happened in everybody's school. So if you go like, this sounds like elementary school or middle school, I'm sorry. Want to cover these, and then we'll talk more on the night sky the next class, where we're actually going to talk about the stars that we can see in the night sky. So I like pictures like this, where literally every pixel is a day of the year, and so you take just a picture out the window, and as you go along, you can just see winter, fall. This is spring, summer, fall. Winter, and so you can see the changing of the seasons, and that comes essentially from the incidence angle of the sun, right? So the sun's rays, if the sun's high in the sky, you only illuminate a small patch, so you get more heat, so you have hotter days. And if the sun's lower in the sky, it has to those same rays have to are spread over a bigger patch of Earth. And so the angle is lower, so you get less light heating up the same patch. I see a question there, so yes.
I know this is more like a weather question than an astronomy question, but how is it that we just have like what we had like a week ago, just this really stretch of like warm days, even though the sun is still like farther away?
Yes, excellent question. So why this works if the Earth is a billiard ball with no atmosphere. And so if you're talking, if we strip out the atmosphere, you get hotter days if everything is like, you get a very predictable temperature because there's no spreading around the heat, right? So I'm heating this patch, and the only way that it would spread from anywhere else is that if the heat goes along the ground, right? Except we have a whole atmosphere, so I'm not heating this patch, I'm also heating the air right above it, so you get like cells of hot air rising there. So you heat, and not every patch of Earth is equally absorbent of heat versus a different patch. So if you've ever been in a small plane, and like I'm talking golf cart sized plane, right, these little Cessnas kind of things. If you fly from over forests absorb heat, absorb the light really well. And if you then go over, say, a parking lot, the parking lot doesn't absorb the heat at all. So basically, it heats up, and the air above it heats up. Sorry, the parking lot absorbs the heat very nicely, and so it starts heating up the air above it, and so that hot air rises, and so you come into one of those cells to bump up. So you get weather, even on smaller scales. So if you do that on a larger scale, for example, the continental United States is a land climate, right? So this is a climate where you have lots of land mass. It heats up either as a whole or it cools down as a whole. So you get pretty extreme hot summers and pretty pretty hot summers and pretty cold winters. However, if you've got places that sort of stay equal, like an ocean, because of the gas currents, etc., and it mixes with the air that we're getting. So if you've got air coming off the coast, the Gulf, for example, and comes up, then we have warmer weather coming in, right? So this is where you switch from a different area. I feel like I've given like a really long-winded explanation on why it was in the 60s last week, but it was kind of, it's not just the amount of sunshine you're getting today, it's also where did the air that you were enjoying right now blow in from. And so if we get what we got today, it's like, yes, the air is coming down from Canada, so it's cold, like it's this Arctic flows, and it comes down, goes over the Great Lakes, picks up a whole bunch of moisture as well, and dumps it down later. So it depends also on the local climate, and local climate happens because of what kind of stream you're finding yourself in. This works to first degree, right? So if you look at completely bald moons or like no atmosphere, then this tells you directly what the temperature is. If you add a atmosphere into the whole thing, that allows you to mix the heat around. So it allows you to move heat from the temporal, so from the equator up to poles, for example. Northern Europe is at a higher latitude than it is here, and it is often colder here than there because they have a constant stream of hot water going from the Gulf all the way up along Iceland over England, and that dumps heat basically there. So you get a temperate climate. All right. Sorry. Yes, atmospheres complicate things massively, right? So we'll get to that when we talk about the rocky planets, because the rocky planets are really fun and interesting because not only do they have rocks to look at, but they have atmospheres almost. And we'll talk about climate versus weather. And so, but to first order, it's like, it's typically colder in these months than it is in the summer, for example. So that comes from the tilt of the axis of the Earth. Who has encountered a picture like this before? Excellent. Okay, so because our Earth doesn't have, its axis isn't aligned with the axis. So if you say like, okay, this is a circle, that's a plane, and that means the perpendicular axis of that orbit is going straight up like this. If I look at the rotation of the Earth, it's at an angle with respect to its orbit. So if you then are in different parts of the orbit, you are in either tilted towards the sun, so you actually get higher incidence of the sunlight, and the south pole tilted away, so this would be the northern hemisphere's summer, and this would be the southern hemisphere's summer. It's really, really odd if you move to the southern hemisphere ever, to then have everybody go, oh, it's the day after Christmas, let's all go to the beach. That is just not a sentence that you usually think of here in the northern hemisphere, unless you are particularly cold resistant. And so if you go from here, you go from winter in the north so you go towards summer, which means that you go into spring, and then summer with the fall, and winter. What I want you to notice that, hey, there's basically an equinox, like a day of equal day-night, and that happens in spring and fall, and then you've got the equinoxes where it's like, okay, it's the smallest, the shortest day of the year. We just had that on December 21st, and then, so that's here, and then we've got like the longest day of the year on summer. Okay, you know the drill. You have to come up with your voting card, right? There's no class where you do not use your voting card. So which of these positions, A, B, C, or D, corresponds with this, which season? So let's pick one. The fall for the fall of the northern hemisphere. So A, B, C, or D. Which one is the fall for the northern hemisphere? Voting in 1, voting in 2, and voting in 3. Okay, I got majority C. This is the winter. There's the summer. So yes, this is the fall. Okay, so what is the winter for the southern hemisphere? What corresponds to the winter in the southern hemisphere? Voting in 1, voting in 2, and voting in 3. I'm seeing it. No, I think almost everybody agrees that it's B, right? The South Pole is right facing away from the sun. Okay, so you can imagine what kind of dates these are. Essentially, you go like, okay, what's the middle of winter here? It's December 20. It's in December, so this will be here in the spring somewhere. So May, and this year will be July, and this year will be fall. And so, but you can imagine that if you are far enough north, and realizing that there isn't that much of a shift here, if you go even closer to the equator, if you're somewhere in Florida, it's like there's not that much difference between winter day, the length of the winter day, the length of the summer day. But if you go further and further north, you get really long days and you get really short nights in the summer, and you get really long nights and short days during this, really long nights and short days in the winter. So just to give you an idea of what happens if you're above the polar circle. So if you're above the Arctic Circle, you can have a day like this, where during the entire day the sun never actually sets. I've had exactly 3 days like that. It really messes with you. So this is the kind of thing where, yes, the sun just basically, you get dusk. And so your internal clock is incredibly calibrated on how much daylight you see, and then especially what latitude you typically live at. So this will basically go, you'll have a moment where you go, it's not that late. Oh, it's 11:30. So, you know, that counts as already passed. So, looking at the images below, which letter A through E best represents winter in the United States? So I've got sunlight going off, and so I've got A, B, C, D, and E. Which instance do we have of winter going on in the United States? One, two, read this. A, classic. And so you can imagine, like, this is our normal situation. But you can imagine that the axes of a given planet with their orbit doesn't have to be nice and perpendicular. It's not in our case. And in the case of Venus, for example, it's not at all. And in the case of Venus, it's a different angle, but in the case of Uranus, it's actually aligned with the plane of the orbit. So you can have all kinds of configurations of what the rotation axis of the planet is versus the plane of its orbit. And that means that you get different seasons. So that's what this is about, but we'll return to when we talk about exoplanets with different kinds of planets. Because you can imagine if you have equal days, great, but then you don't have seasons. So the kind of life that developed on Earth wouldn't really thrive there because it expects to see seasons. The kind of things that you have extreme seasons, for example, that might also not work as well. So let's see, we've got which of the locations identified with an X, right? So we've got a bunch of X's, and here's the axis of the planet, and so we've got sunlight coming in, so 45 degrees, 0, 23, 90, and 23 degrees again. Which one of these would experience the coolest temperature over the course of one day being one planetary rotation? So see where the X sits, and imagine which one of these would be the coldest. Which one would be the coldest temperature of the whole day? 41, 42, 43. Not as many people voting as last time. I got a majority D, but it's sort of scraping by. Imagine what happens to this X, right? It's always in the nighttime. So this is a planet that has one completely hot side and one completely nighttime side. And if you, depending on where you are, that's where you either have full-time day or full-time night. Okay, so you have another question, Mike? So which one of these would correspond to the, let's see, summer in the northern hemisphere? Which one would be Earth in summer during the northern hemisphere? One, two, 23. Excellent. I got a mix of pronouncements, so you know what this means, right? Everybody, turn to your neighbor, and even if the two of you agree, I will confuse you at some point, right? I wanted to get to this point. Turn to your neighbor, and even if the two of you agree, explain to them why your answer is correct. We've got 90 seconds to do so.
He said summer.
So that's a B. Just because X. I heard the question.
Yeah, see, I'm not looking at the location, so I'm like looking at like the hemisphere. Right? What part of this is the solar?
Yeah, that kind of makes sense, but like,
That's like when the sunlight's facing there, that might later then it's like
I guess it's summer.
it just might
No
be
way
good.
it's
It might just be a graphic interpretation of this.
I don't really know. I just don't like. I see what you're saying. I don't think it's either just because we don't have it.
It's like
One, Volume 2, and Volume 3. Oh, fantastic, you all convinced yourself? Yes, that's it. So if I then go Southern Hemisphere, which one is that one? Volume 1, Volume 2, and Volume 3. Let's see. All right, this is an easy one. If it's the Earth, the inclination has to be 23 degrees, one of these two. And so this is the northern hemisphere's summer, like you've got a long day. And here's the southern hemisphere's summer, because you get a long day here, so which means that X is now experiencing winter. I think we got most of this. You've had this maybe in school, bits of it. But it does explain that even if when we talk about Earth-like planets, you'll hear, if you keep an eye on the news, you get like an Earth-like planet has been discovered. This is sort of the holy grail at the moment to find that Earth 2.0. The problem is Earth is a very specific environment, right? And one of these things is that it has seasons because of that air conditioning. And actually determining whether or not an exoplanet is maybe this, because that would be fantastically inhospitable, versus something like this. This would just be, yeah, there's more extreme seasons. Well, okay, we can adapt to that. There's a difference between whether or not you can have life that is compatible with life on Earth, on a planet this way, or one with similar seasons or not. And that means you have to find out a lot more about these than just whether or not it's at the right distance. So we can sort of summarize the following. Earth's rotation gives us the day, Earth's orbit gives us the year, and then the tilt of the Earth's rotation gives us the seasons. So these things are easy to understand, but these are also the first things that, as if you're a band of hunter-gatherers following the bison, or you are the first civilization to, or the second or the third, to try agriculture, all these are important to keep track of, right? You want to know what the length of the day, or like time, you want to see what the year is, you want to keep a calendar, and you want to know when it's planting season, or the bison is supposed to return, right? So this is the stuff that you want to keep track of. And so I have a little group work about weather, which is really all about that incidence angle and how much heat you then get per latitude. You can imagine that having a naked eye astronomy sort of is directly linked to the kind of astronomy that you could have done for the longest time, right? We've done observations of our Earth-Moon system. We've used it as a calendar. We've used it as a clock, and we've used it as a warning when, by the way, like this kind of lore can be incredibly useful if you're a beginning civilization. You'll notice that there's something really fun. Should dig it out. Cuneiform. So the Assyrians and Babylonians had astronomers on the payroll, and the reason for that was, well, these were people that were actually keeping the calendars and were keeping the clock for everybody to say like, yeah, now is planting season, or the two, the Euphrates and the Tigris are about to flood, so we better, or they're late, so we might want to wait with planting season. So weather versus climate comes up again when we talk about, again about the rocky planets, and we talk again about this, when we talk about the exoplanets. Because predicting what kind of weather they have, whether or not they have lots of clouds, whether or not the angle is the same as it is on Earth or similar, that is challenging. actual phases of the moon is what inspires the idea of the month, right? So about 30 days, 27 days of a cycle like that. But we also have cycles within biological systems that follow that. Again, because most of life sort of started in tidal pools, so it naturally had a tidal, expected tidal cycle. Let's see if this actually goes. Yes. So if you, this is a small satellite that actually has orbited all of the moon, so you get a full moon picture, and so you can. This is our nearby moon, but this is the European Space Agency, so this is their little satellite. You can actually identify all the lakes or basins there, but all of this is, the moon is completely dead. It's just one giant rock, and you can see the craters that have built up over time. You can also see that this part has lots of craters, and then there's areas that you don't have a lot of craters, and so this helps with the. So here, this is the crater-rich part, and then if you wait a little bit, you get to the part that I think is facing us. Here you go. You've got those darker spots. Those are lava lakes that built later, and so you can sort of gauge the age of a surface this way. I like to talk about this also when we talk about terrestrial planets. You can sort of see how long on a geological scale a surface is basically by how many scars it has, how much it has been hit by asteroids. So the moon, yes, most of it is incredibly old. The surface is very, very old, and some of it is younger, but most of it has been like this for a long time. And so we can only see one side of this, right? So if you go to the far side, not the dark side, but the far side of the moon, the other side of the moon is the one that we haven't actually seen much. So if you look at the Moon-Earth system, I like this little NASA animation because this is, you can see the Earth rotating quite rapidly, and this is the moon in its orbit that isn't quite aligned with the orbit plane of our Earth and the Sun. So you have the shadow of the moon, and it most of the time misses because it goes below or above the planet. But sometimes it just hits the Earth, and that's when you get an eclipse. So that's when you get solar eclipse. The sun's over here, and so the shadow of the moon just manages to hit the Earth. It is a complete coincidence that the size of our moon and the distance of our moon is just right to cover the disk of our sun. That has nothing to do with any kind of design. That just happens to be the case. And when we talk about tides, we realize that the moon keeps going further and further, so there's going to be a time that it's going to be too far away to cover the disk of the sun. So we're just living at a lucky time that we have a moon large enough at just the right distance, because the sun's 400 times bigger on the sky, bigger in diameter, but it's also 400 times further away than our moon. So it just matches up. We're just lucky that way. So you can have total solar eclipses most of the time. So you see like this little slight. Can you see the shadow there a little bit? Like you can see the central shadow just ends at a point. So just in that point, which is just a few miles across, that's where it covers the sun completely. And on either side, you get a partial solar eclipse. And that's the thing. Who here has seen either the 2017 or the more recent eclipse? Did you see the full totality, or did you see it partial? Partial. Yeah. So if it's partial, you shouldn't have looked at the sun like at the whole thing immediately. Like, did you get the glasses? Please tell me that you got the glasses. Okay, right. Yes, fantastic. Because then you're still looking at the surface of the sun, but if you're in the totality, it covers it all completely. So it's suddenly dark, right? So there's a real difference between there's still 3% visible of the sun, that's actually pretty light, versus if you cover it completely. And so if you have the right alignment, and if you are in the right part of the orbit of the moon, right? So where it is in between the intersects the orbital plane of the Earth, that's when you can have a total eclipse. Not any time else, and only on a very small patch of the Earth. Okay, so this is the kind of pattern that you can realize earlier, but this repeating pattern that you have to have, both the orbit has to be at the new moon kind of phase of the lunar cycle, and it has to be right in the part where it passes through the orbital plane of our Earth. When both of those things align, that means there is a pattern to it, but it has to repeat over many, many times before you notice it. And so you have to look at the new moon, waxing crescent, first quarter, waxing gibbous, full moon, waning gibbous, third quarter, waning crescent. I'll talk about all these phases in a second, but these are, and not in the least because it has one of my favorite words in the English language, which is gibbous, just fun words to say. And crescent we can all remember because crescent rules. But so you start with no moon because basically it's lit from behind, so we're looking at the dark side, and so that's over here, dark moon, and then a little bit, right? It's just a one little sliver you see, so you can have this crescent. This is a waxing, meaning that it gets bigger. So waxing crescent till we get to about this is about halfway, so that's the first quarter. You can actually see the first quarter, and then it's gibbous, and gibbous means it's over half lit, right? So gibbous just means a little bumped out on this side. So it's more than half the part that I'm looking at is lit up, and then gibbous, and at some point you get half full moon, and then there's a little sliver missing. So it's still gibbous, but now on the other side, and it is now waning. It is becoming lesser and lesser and lesser until you get about this here. This is the fourth quarter, and then it's a crescent again, so it's a waning crescent, and then back to full moon. That's a lot of words that I just threw at you, right? Two new words like gibbous, crescent, with waxing and waning. The thing is, this is a nice pattern that you could keep, and so you can use it as your calendar. And so ancient Babylonians, for example, noticed that this was, here's the pattern, but also they noticed when these eclipses happen, which happen much more rarely. And so they started noticing the pattern in the pattern, and actually figured out a way to predict this. Imagine you were an ancient Babylonian astronomer, and you have found a trick to say, oh, there's going to be an eclipse. The sun is going to disappear for a second. Are you going to cash in on that? Of course you are. You're going to use that as the sun is about to disappear. And you're going to use that trick to say, oh, and you should definitely listen to me when you're planting the seeds or when the calendar is. And I should really use a pair. They already figured out that there was a pattern. They didn't quite know why there was a pattern. They didn't have the whole, we're orbiting the sun, but they noticed the pattern already enough to make predictions, to both make lunar eclipses and solar eclipses to make a reasonable prediction. Okay, so how long does it take to complete a full cycle of moon phases? About a day, about a week, about a month, about a year, or none of the above. Voting in 1, voting in 2, and voting in 3. Yes, exactly. This is where our month comes from. So why don't we get like a nice synchronization between our months and the lunar month, right? Well, the number of lunar cycles don't fit quite in our year, so it will shift anyway. And for reasons we've never made our each month get equal length. And the Romans sort of filled that out with all our months are, I think there were 28 days or 29 days, and they just filled the rest of the year with one big party, which I think is not the worst way to solve your calendar problems. Just go like, we have a couple of spare days. Oh well. But everybody sort of solves their calendar keeping in a slightly different way. So here's another question for you. The moon is visible only during the night. Voting in 1, voting in 2, and voting in 3. Okay, thank God. You've all noticed the moon at some point in the middle of the day, right? It doesn't matter if it's up, it's big enough and bright enough, that as long as it's illuminated, you can see it. And so, what we think of is like, here comes the light of the sun on this side, and so the moon is always half lit. It really depends on where we are looking at it to see if we're like in third quarter, waning and waxing, or in the moon. So if it's over here, we get a fully blocked, lit from behind a moon. So the dark side of the moon is something that we occasionally get to see. The far side of the moon, we never get to see. It's tidally locked, right? So it only has the same face as facing us. And so here's a question: if the moon is full of phase today, how many of the moon phases shown above would the moon go through during the next 11 days, right? So a full cycle is 27. So if only 1, 2, 3, more than 3, or none. One, two, you know what the deal is. Turn to your neighbor, even if the two of you agree, explain to them why you're right. Like makes sense.
It's like a really good read at the 2 weeks. But like, you get 3 weeks at least.
One, two, three. Okay. It's funny to see like little islands pop up, like people have convinced them it's B, C's, islands of that. All right, so if it's full moon, which one is right after the full moon? That one, right? It's starting to get darker on this side. It's no longer full, so that's definitely one that we can see. This is right as it's waxing, right? So this it waxes from right to left. So waxing. So first quarter, and this is waning. So it can't be either any of these. So this one and this one, we have 2 that we can do with this one and that one after full moon. Right? You see the whole disk and it starts to get darker from one side. Yes.
Would it not? Which one you said it? You said it could be the waning crescent.
So let's see if I can go back to here. Yes. So we've had full moon.
Right.
And then we start losing on this side, right? So we have this one, I think, is visible in the whole.
Right. So I was
This is
wondering-
27. This is sort of like close to 30 days. I'm doing 11 that is less than half this, so I can't even get to here. But I should see something like a gibbous full moon where the dark side is on this side, and maybe I get to here for the half, the third quarter. So if I now switch really fast to here. This is one we can expect to see, and as you get more of the moon disappearing, you can get to see this third quarter one. That one is the first quarter. That's well before the full moon, and this is also before first quarter. You don't see that one, and this is after third quarter. So it will take longer than 11 days to get there. Thanks for asking, because that forces me to explain, which is good. So much appreciated. I appreciate the people who nod, but I also appreciate the people who ask questions, because I know we're going to go. Okay, so it gets us a month pretty clearly, and so hopefully I can get the planetarium. Drew is not here, so if I break the planetarium, don't tell him. Get it done. starting with our Earth, with our moon, land, well, somewhere in the continent of the United States. I think they just pick headquarters for the people that make this, but that's all right. And so we're facing north, right? So we're putting our noses toward where north is, and west is to our left, east is to our right. Ignore the stripe here. That's where the two projectors come together, and they're a little out of whack. We haven't gotten anything better than this. And we get sunrise. Here we go. In the east, southeast from the sun. So the sun is behind us. If we're looking north, the sun is behind us, rising in the east. So now we're going to turn around. Gives you an idea of how we can turn around without turning around here at the planetarium. So we're going to put our noses facing south. And so as we face south, we always start it facing north with a planetarium, just to like, okay, we start here and then we turn around or we turn to a particular location. And as you get, like you have the sun rise and set because, you know, this is fall-ish, so you can see the sun set, and at the same theme, you can have clearly sped up time. Oh, look, there's our friend Orion. And so the stars rotate from our perspective. And if you're facing south, and there's the moon. So the moon rises into view, and because we're now looking at full moon, the moon and the Earth and the sun are basically along one line. So this is fully illuminated. It's a new moon, right? So we're seeing the full new moon. And as we keep going, so sun and Earth are along one line right now. So that as this fades, on the far side you get the rise of the sunrise. Where is no sunrise? Oh. Okay, so now we've sped up so even more, and as we we've blown up both moon, well, definitely the moon, so you can see the phases better. And so as the moon gets sort of chased by the sun, there's plenty of stories from different tribes, like the moon is slowly being overtaken. You see the moon fade. You know, there's basically a hunting story to go with this, where the sun is the hunter and the moon is the prey, or the disciple, or what have you. And as they're getting closer together, you realize that yes, there is now the moon is. This is this is third quarter, where only half the moon is now illuminated in the middle of the night, and so, or in the during nighttime. And as we keep going, you now see the moon a little bit during the early morning. So you see the morning moon, which is waning, and so now it's a waning crescent, and the sun is overtaking, seems to be overtaking the moon during the day, and the moon seems to be diminishing. Like there's these stories that the sun, often a male god, that just basically takes bites out of the moon, and at some point you now are doing a new moon, or almost new moon. You don't see the sliver anymore, so the moon. This is new moon. Essentially, we're now looking at the dark side of the moon. So you don't see it during the day, you don't see it during the night. New moon nights, there's a few nights where you basically get no moon because it's fully illuminated from the back, so we just get the dark side. In astronomy are fantastic nights because you don't have a bright object sitting in the night sky, sort of pestering any deep photography, any deep pictures you want to take. So if you're at an observatory, the dark nights are the 4 nights around new moon that you get full darkness and you have a much darker night to observe with. So those are the most coveted nights. But if you go like, I can sort of tolerate a little bit of moonlight, then you get the gray nights where you can actually see bits of the moon during the night. And so is now not visible. We labeled it, we scaled it back down, and we keep going. And this is part where like you get these where the story sort of reprises. It's like, yes, but the moon goddess actually regenerates or pops back up, because as the distance between moon and sun, the angular distance, the distance on the sky seems to improve, you start seeing more and more of the crescent of the moon there. And so now you have a waxing crescent. So you, here we go, yes, there's our waxing crescent moon. So again, now you see it during the day or in the evening, you see the moon crescent come up, and until we get to first quarter, which happens now. And so now we have this side of the moon illuminated, and that's first quarter. And so we can keep going until we're back to full moon, where we get a gibbous moon, where now it's a little fatter than half. So you can see that it is a sphere, and so you can see that it's a little thicker than on that side. And so now the moon sort of regenerates, and the moon is chasing the sun. And so this whole like flip between a chase between chaser and chasee is very much part of various cultures' moon sun stories. Right, we get to full moon. Okay, so this is the part where you actually see the full disk of the moon, and so now we're reorienting back to north. If you are a little woozy by this, just close your eyes for a few seconds. We should be coming back to north. And so all this is happening now behind us. And oh, we're flying to orbit. Okay. You see all the cities of North America. I think we're going to see this from, this is the scene where we actually see this from, okay, here's the orbit of the moon, the orbit of Earth. Of course, the Earth, you can see the Earth rotating, and you can see the level of illumination. Yes, here we go, there's the third quarter. Keep going. We blow up the moon a little bit so that we can actually see, not really blow up the moon, but just see what we're doing. And as we go to new moon, it's fully illuminated from the back. And now you just look at the dark side of the moon. Again, if it's dark side of the moon, those nights you have the darkest nights. You can spot dimmer stuff in the sky much better. As we keep going, we now get the crescent on the waxing side, so waxing crescent on first quarter, and then back to full. So, I'm not sure if I said this already, but it always strikes me that the moon is actually, I mean, sure we made it a little bigger today, but everything, our moon is actually quite large for the planet it's orbiting. The only other pair is sort of Charon and Pluto, and they're sort of orbiting each other. They're sort of a twin situation. So our Earth is unique in the fact that it has this massive moon compared to its size. And so that might be a reason that that might be important for the kind of life that we have here on Earth. I mean, it gives us tides, it regulates the day, it might catch the occasional asteroid that otherwise might kill us. So maybe having a really big moon is an important part of your having life on planets. But for our particular instance, it is also a very useful way to keep the time and calendar. All right, and it goes about the rarity of eclipses. I was trying to say that before, but essentially because the size of on the sky, so the angular size, not the physical size, but the angle that covers on the sky, and the moon's angular size, how many degrees it covers on the sky, are just about the same. You can perfectly cover the disk of the sun with the disk of the moon if you have that rare alignment of both Earth, Moon, and Sun. If you're on the far side, the shadow of the Earth is a lot bigger than that of the Moon, so it will cover the Moon quite nicely, so you get lunar eclipses. And as you can see, this is the green line here is the plane of the orbit of the Earth. This is where all the planets, the ecliptics, and this is where all the planets are. And the orbit of the Moon isn't quite in the same plane. It's a little tilted, meaning that if it's below here or if it's above here, you don't get that perfect alignment, and you get a partial lunar eclipse. Solar eclipse. So you can have where it's partially covered, or maybe even if it's on a particular part of its orbit where it's now too far away, it can actually be an annular eclipse, so you actually get a ring of fire around the Moon. So actually getting full total eclipses is very rare. The lit up version here is the shadow of the Moon, and the shadow of, sorry, this is the shadow of Earth, there's the Moon, that's the shadow of the Moon. I've hit the space bar, but what is happening? Nothing. Okay. Right. Can you tell I'm nervous to break the universe and have to explain it to Drew? So far, so good though. We're having a look at the Moon, closer look at the Sun at this point. So if you're wondering, yes, the Sun has cycles on its own, right? So it has completely different cycles. One of them is the actual orbit of the Sun, which is about 30 hours. So it actually has nothing to do with it. But we don't get the day or the month or anything because we don't notice that part, right? It also has an 11-year cycle where, especially these dark spots that we've been spotting for about 300 years now, they appear and disappear on an 11-year cycle, and there's also a slightly more subtle 30-year cycle. And so the cycles within the Sun might also affect things on Earth, but much more subtly. So we don't get things like a calendar from that. This is not something we notice, but it is something that we'll notice as a civilization because the solar storms happen on those 11-year cycles. So it's sort of a season, but this time on the Sun itself. So you can get more solar storms, more activity, and so if one of those solar storms hit hit this one here particularly, we might have some issues with our electrical grid, and definitely we should save most every satellite on Earth. This is the part where if there's a coronal mass ejection and it's going in the direction of Earth, that's the part where the astronauts in the ISS basically hear a klaxon, they jump into their little Soyuz and hightail it to Earth because it's absolutely not a good idea to be in orbit at that point because all your electronics might get fried and also you. So space is not a very welcoming part of living. So this is the part where their atmosphere, once again, is helping us protect against that kind of stuff. So every rocky planet and every planet around every star has its own year, and depending on how it orbits, so how fast, not just its orbit, but how fast it rotates, it gets a day and as well. So you have very different days on, for example, Venus and Mercury. The day on Venus is longer than its year because its rotation is a year. On Mars, however, you get something that is 22 hours long, so it's actually pretty close to a day on the Sun, on Earth, which is it's called a sol, and it's the kind of thing that makes us think that Mars might be very hospitable to us living on there. But there are some notes there. We'll get to that eventually. So depending on where you end up living in the solar system, you might have a different year, a different day, and a different calendar altogether. show you the lunar, like the sun moon chasing, because that's a very big part. Okay, we don't need to do the rest of the solar system. We have been there. So, watch out, the lights are going back on. Okay. This is me trying to do this in between. No idea how much that got captured on the recording. So anybody who's watching this from home, I'm sorry if you just saw some white grayish orbs fly by. That is the best my iPad can do. Is that good? Bad? Sounds bad. All right. So, almost done, but I'm going to ask you one question here. Who here has seen the movie Moana? I love the fact that it came out just long enough for everybody to have seen this, just the right age, right? My kids loved it as well. I loved it because I have to make it a little darker here. Yeah, you can't quite see what she's doing here, but you know, what is she doing here? She's looking up and holding up her hand. Anybody remember the scene or figure out what she's doing? Why is it blue here? Oh, right. There we go. Can you sort of see the scene? Yeah, I see Grumpy Maui. Right, so what is she doing here? She's high-fiving the sky, she's waving at another boat, she's gauging the wind, or she's doing wayfinding or navigation. So this is something that we're going to talk about. Why was astronomy basically a tactical art a few hundred years ago? So I mean, 1, 2, you all remember the scene, fantastic, thank you. Yes, she's wayfinding, she's navigating, and I love the fact that you get this scene here where you can measure, she's doing this L shape at the 3, the belt of Orion, to figure out how high above the horizon Orion is at that point. So this is a trick you can do. And so this is a very good distinction to make when people talk about astrology, where it's basically, oh yeah, the moons are over, sorry, Jupiter's over here, versus wayfinding, which is a sort of lore that tells you where you are. And it's quite amazing to consider how big Pacific Ocean really is. If you see Earth from, above the Pacific Ocean, you really would think that it's mostly water. There's just a few islands that you see at the edges. And so between the lore of, hey, this is how you use the stars to figure out where you are latitude and longitude wise, it also tells you it's a bunch of other pieces of lore, like yes, if you feel the water, if you go warm or cold, what kind of currents. So it's a combination to figure out where you are. But considering the size of the islands and considering the size of the Pacific Ocean, it's kind of amazing that these boats made it at all, right? Considering how often various Western navigators managed to, well, essentially steer into a rock. And so the thing that she's doing there is literally measuring an angle on the sky. And I think we've talked about briefly before the size of about 1 degree, so you've got 360 degrees all around on the dome, right? This is 360 degrees. 1/60th of that is a arc minute, and 1/60th of that is an arc second. So I want you to briefly consider this is not base 10, this is base 60. Everything else we do is base 10. Why are angles and hours and minutes in 60? Does anyone know? That's how the ancient Babylonians set it up, and everybody liked the system, and so we just stuck with it. No one can read Babylonian anymore. There's like 5 different civilizations that came since. It made so much sense to measure angles that way that we've used base 60 angles ever since. Ancient Arab world, ancient medieval Christian world, and even the Chinese world picked up the base 60 So we have, and it's not a coincidence that this is minutes and seconds, because you can also measure this in 24 hours, because that's how long it takes to rotate. So you get hours, minutes, and degrees as you go through. So on Thursday, we will go talk about how we actually find our way on a sphere. It's not the same as on a map. If you have a big sphere, you need to divide it up into longitude and latitude. This all comes back to how you find your place on Earth as well. I know none of us think about that anymore because we have GPS, and this helps a little bit. But if you don't, you have to figure out from the stars where you are on Earth. So, you guys heard about navigation by stars other than from Moana? But Moana's a good one to start. So we've used celestial navigation, and also that makes an important part. We have a Navy and a British requirement. So, all right, so this is where I want to stop for today. We'll talk to you on Thursday about celestial coordinates and night sky. See you Thursday. I'll bring up the lights, and then please put the rubric. Thank you very much for coming, because I know it wasn't exactly the best day for driving to come in. All right.